Hello friends, welcome to my channel Computer Engineering Made Easy and I am Anindita. In this tutorial, I will discuss about the concepts of heap memory and how we can use it for dynamic memory allocation. Heap memory is one of the various segments of the memory pool in C. I recommend watching my tutorial on memory pool in C, whose link is given in the top right corner of the screen prior to watching this video. Moreover, the links to the codes that I am using in this tutorial will be given in the description box, so please feel free to download them if you need. The memory pool in C is divided into predefined sections, and each of these sections have specific locations with respect to their memory addresses. The heap is a large pool of memory that can be used dynamically, that is, during program execution or runtime. This memory is not managed by the CPU and requires management using specific system-defined functions. Unlike stack, the heap is large and is usually limited by the physical memory available. Variables created on the heap are accessible anywhere in the program irrespective of the scope with the help of pointers. Now, before we learn how to handle dynamic memory allocation, let us first understand why we need it. Say you were asked to write a program that stores the entrance exam score of 500 students who has joined your institute along with you in the first year. Now, in the next year, it is expected that some more students will be joining your batch, but you don't know exactly how many students. So what can you do? One of the thought process can be that since 500 students joined in the first year, another group of 500 students may join in the next year. Assuming this, you can consider an array of size 500 plus 500 equal to 1000 for storing the marks of the students. Similarly, your friend might have had a different thought process and may assume that 500 might be too big a number and maybe 100 students might join in the next year. So, he considered the size of the array to be 500 plus 100, which is equal to 600. Now, if you have m students in your class and all of you are implementing the same program, all m of you will be assuming different values of n. So, we can categorize your assumptions into three broad categories. Category 1, where the assumption exactly matches the intake in the next year, which can be referred to as the best possible case or ideal case. The category 2 may be where the intake is actually higher than the assumed value of n. In this case, there will not be sufficient storage space in the array to store the information of all students. In the third category, we have the cases where the assumed value of n will be higher than the actual intake. In this case, the memory assigned to the array will be wasted. Now, if you are dealing with a system where there is no memory constraint, this approach might be acceptable. But in cases where we are designing the program for a memory constrained device, this wastage is going to affect the performance of the system significantly. Hence, we need to acquire the memory according to our requirement so that neither there is shortage nor there is any wastage. Dynamic memory allocation helps us achieve this solution. It allows us to increase the size of the array at runtime so that we can acquire the exact amount of memory that will be necessary. To implement dynamic memory allocation in C, we need to know about the common functions that are responsible for allocating as well as deallocating memory dynamically. In C programming language, the commonly used functions are malloc, calloc, realloc, and free. Out of these functions, malloc and calloc are responsible for freshly allocating memory from the heap, while the function free takes care of the deallocation. Since C does not have any automatic garbage collector, the function free needs to be executed explicitly to deallocate the memory allocated by malloc, calloc, or realloc. And the deallocated memory will then be added to the available memory pool for further use. Realloc is responsible for reallocating already allocated memory. It works only if the memory was allocated initially using malloc or calloc. It does not work for static memory allocation. For example, say we already have an integer array of size 5 created dynamically using malloc or calloc. We can use realloc to change the size of this array if required. Whereas, on the other hand, if we have an array created by writing int arr5, this statement on execution will create a static array in the stack memory. In this case, realloc will fail to reallocate memory to arr. Now let us take a deep look at the working of each of these functions, starting with malloc. Malloc. The term malloc is basically a short form for the term memory allocation. It allocates a single large chunk of memory of the size that is passed as parameter. It returns a pointer of type void so that it can be typecasted to pointer of any other data type as required. For example, if we want to allocate memory to a 5-celled integer array dynamically, we write malloc 5 into size of int. Here, size of int returns 4 and 4 multiplied by 5 gives 20 bytes, which is the total amount of memory required for a 5-celled integer array. The starting address of the block is returned by the malloc function. Now, malloc by default returns a void pointer. But since we are returning the address of an integer, the void pointer is typecasted to a pointer to an integer. In order to do this typecasting, the int star within the brackets is written prior to the malloc function. Now, since an address of integer is being returned, we need a pointer to an integer to hold the address. Hence, int star ptr is placed on the left-hand side of the assignment operator. As shown in the figure, the variable ptr will be a part of the stack memory since it is a local variable, while the memory chunk will be in the heap memory. The only link between them is the address of the 0th cell of the array, which is located on the heap, will be stored in the stack variable ptr. Now, if for any reason the malloc function cannot allocate the memory that has been requested, it will simply return null instead of any memory address. Now, once the dynamic array has been created, in order to access the elements of the array, we need to learn pointer arithmetic. Unlike regular arithmetic, the data type plays a significant role in case of pointer arithmetic. Incrementing a pointer variable ptr by 1 will actually cause the content of ptr to be incremented by the size of the data type to which it is pointing to. Similarly, if we want to increment the pointer by n, its value will get incremented by n into size of the data type to which it is pointing to. For example, on executing the statement int star ptr equal to int star malloc 5 into size of int, a 5-celled integer array is created whose starting address or the base address in this case is say 0x0231D8. This address gets stored in the variable ptr. The assignment creates the link between the variable ptr stored in the stack memory and the memory chunk in the heap memory. Since ptr is a pointer to an integer, on incrementing ptr by 1, that is on executing ptr++, it will increase its contents by 4. Here, 4 is considered to be the size of an integer. Thus, on executing ptr++, the content of the variable ptr will become 0x0231dc. On further incrementing ptr by 3 will cause the increment of the content of ptr by 3 into 4, which is equal to 12. Thus, ptr will become 0x0231e8. The addition that is happening here is obviously hexadecimal addition. Similarly, when decrementing ptr by 1, we actually deduct 4 from ptr. This is because ptr is a pointer to an integer and an integer takes 4 bytes. Thus, on executing ptr minus minus, the value of ptr changes from 0x0231e8 to 0x0231e4. And on deducting 3 from ptr, actually 3 into 4, which is equal to 12, gets deducted from it. Thus, the value gets changed from 0x0231E4 to 0x0231D8. Note that every increment of the pointer variable by 1 is actually making it refer to the next cell in the array. Similarly, on decrementing the pointer variable by 1 is making it point to the previous cell in the array. Pointer arithmetic does not include pointer multiplication or pointer division. Now let us take a look at a case where PTR is a pointer to a character instead of an integer. We know that a character takes 1 byte of memory. Accordingly, when we execute PTR++, the value of PTR now in this case changes by 1 into 1, that is 1. Therefore, the PTR value gets changed from 0x0231D8 to 0x0231D9. Similarly, when we increment PTR by 3, it now adds 3 into 1 to the current value of PTR, that is 0x0231D9, to get the resulting value 0x0231DC. When PTR is decremented by 1 by executing PTR minus minus, the value of PTR gets decremented by 1 into 1, that is 1, and thus PTR now holds 0x0231dB, and on further decrementing it by 3, we get 3 into 1 equal to 3, which gets deducted from PTR, resulting in 0x0231d8. Note that even in this case, incrementing PTR by 1 makes it point to the next cell of the array, while decrementing its value by 1 makes it point to the previous cell of the array. Now let us take a look at a program that not only creates a one-dimensional array, but also stores and retrieves values from its cells. First, we will see the basic benefit of dynamic memory allocation. Static arrays are created without considering the requirement of the array. Usually, we keep the size of the static array significantly high so that there is no shortage of space. But eventually, it will lead to wastage of memory. Dynamic arrays are created at runtime while considering the requirement of the user. Here in this case, we first take the desired size of the array as input from the user. Say the value entered is 5. Next, we create a one-dimensional dynamic array of size 5 using the malloc function. In order to store and retrieve values from the array, we will use loop with I as the loop variable. For storing data, I is initialized to 0, and since 0 is less than 5, the control enters the first loop. The printf statement asks the user for input, and the scanf statement stores the value provided as input in its appropriate position. Note that unlike the scanf statement used to take the value of n as input, we have not used any ampersand here. This is because ampersand is the short form of address of. And when we wanted to store the value provided as input in the address of the variable n, ampersand n provided the address of the variable n where the data was stored. Now in this case, we want to store the value provided as input by the user at the address of the 0th cell of the array. Now who is holding the address of the 0th cell of the array? Note that ARR is holding the base address of the array. We get the address of the ith cell of the array if we simply add I into 4 to ARR. 4 because here we are dealing with an integer array and size of an integer is 4. So if I is 0, the address of the 0th cell is given by adding 0 into 4 to ARR. 0 into 4 gives us 0 and ARR plus 0 gives ARR. Thus, the address of the 0th cell of the array is given by ARR plus 0. Since ARR plus 0 is itself the address, we skip giving any ampersand here. Now in case we want to store the value in the 1th cell of the array, we would require the address of the 1th cell. Now the address of the 1th cell is obtained by simply adding 1 to ARR using pointer addition. That is, on adding 1 into 4 equal to 4 to the current value of ARR using hexadecimal addition, we get the address of the 1th cell of the array. Similarly, to get the address of the ith cell, we simply perform the pointer addition ARR plus I, and we do not need any ampersand over here. Once the data entered by the user is stored successfully in the array, we can move on to displaying the contents of the array. In order to do so, we need to traverse the array once again, and hence we require a loop. I is again considered as a loop variable and is initialized to 0. Now, as we look forward to display the content of the 0th cell of the array, we need to write star of ARR plus 0. ARR plus 0 provides the address of the 0th cell of the array, and the star before that is read as content of. Thus, star of ARR plus 0 provides the content of the 0th cell of the array. Similarly, to get the content of the 1th cell of the array, we add 1 to ARR using the rules of pointer addition, and then we extract its content by using the star operator. Thus, using this method, we can get the value of the ith cell of the array by simply writing star of ARR plus I. In this program, while displaying the content of each cell of the array, we are also displaying the address of each cell of the array. Note that in order to display the address, we are now using %p instead of %x. Now %p is used to print the pointer value and %x is used to print the hexadecimal values. Pointers can also be displayed using %u. If we print some value using %p and %x, no major differences will be observed. The only difference is that the %p will print some leading zeros, while %x will print a 0x before the actual memory address. So, on displaying the output window, we can see that the address 0x7c3280 is displayed as 007c3280 and so on. Note that the address of the consecutive cells differ by 4 because this is an integer array. It also indicates that the cell is occupying contiguous blocks of memory. Now, after we are done with the array, another important step that needs to be done is the deallocation of the memory that was allocated from the heap. We know that C does not have any automatic garbage collector. Hence, the deallocation needs to be done by the programmer explicitly once the memory is no longer required. The free function is therefore called with the pointer variable as parameter, which is pointing to the memory chunk assigned from the heap. In this case, ARR is the pointer variable which is linking the stack memory to the heap. It is also the variable that is holding the base address of the memory chunk assigned by malloc. Hence, it is passed as a parameter to the free function. On executing the free function, the link between the stack and the heap memory gets broken. The values of the cells in the heap memory get replaced by garbage value, whereas the variable ARR still holds the base address that was assigned to it. Now let us take a look at what might happen if we do not free the memory. Say we have 17 bytes of memory, and say we first execute something like P1 equal to malloc 4. This assigns 4 bytes of memory to P1. The memory maintains a pointer which marks the beginning of the next available memory slot from where allocation might start. Accordingly, when P2 equal to malloc 5 is executed, memory is assigned and the available memory pointer changes its position. Further, when P3 equal to malloc 6 is executed, 6 more bytes are assigned, thereby shifting the available memory pointer. Now, when free P2 is executed, the memory assigned to P2 is considered to be free and gets linked with the available slots. So next, when P4 equal to malloc 2 gets executed, 2 bytes are allocated and the available memory pointer now points to the memory slot which was initially allocated and then freed by P2. At this stage, if another memory allocation request is made up to 5 bytes, the memory address stored in the available memory pointer will be returned, otherwise null will be returned. If you want to learn more about this topic, you take a look at the topic of memory management in the subject of operating system. Now let us take a look at the next function, that is calloc. The term calloc is the short form for contiguous allocation. It takes two parameters, namely the number of memory blocks and the size of each block as parameters, and assigns memory chunks accordingly. Calloc 5, size of int assigns 5 contiguous memory blocks, each of size of an integer, that is 20 bytes in total. It takes the number of blocks as a separate parameter because it assigns 0 to each of the blocks before returning the starting address of the blocks to the stack memory. If it cannot allocate the requested memory from the heap, calloc returns null. Creating and manipulating a one-dimensional array using calloc is very similar to that using malloc. The only difference is in the statement where the calloc function is called to allocate the memory dynamically. As you can see, unlike malloc, calloc passes two parameters. The first one is the number of blocks, which is same as the number of cells we want in the array, and the second parameter is the size of each block or cell. This depends absolutely on the data type of the array that we want to create. Thus, if the user enters the value of n as 5, the calloc function will pass 5 and 4 as parameter and will allocate 5 contiguous blocks of 4 bytes each to the pointer ARR. Also, if calloc is used to allocate the memory, each of the cells of the array will be initialized to 0. Thus, on executing the program, we get an output somewhat like this. Note that the 5 memory blocks of 4 bytes that has been allocated are all contiguous in nature. This is clear from the memory address of each block, as the difference in the address of any two consecutive blocks is 4. Let us now see an example where we will create two arrays dynamically, the first one using malloc and the second one using calloc. We will then see what are the contents of each cell of the two arrays. We are taking this example to see whether calloc actually assigns 0 or not. In the output for malloc, note that the first two cells are holding garbage while the other cells are holding 0. Let me tell you that even the zeros over here are representing garbage values. If run on a different machine or at a different time, the values will all get changed. On the other hand, the calloc function initializes all cells to 0 by default. It is a job of the function itself. It will never change irrespective of the time or machine on which it will be executed. Thus, unlike malloc, calloc takes two parameters and assigns 0 to each memory block. This assignment operation uses up some CPU cycles, and hence calloc takes more time than malloc. Both malloc as well as calloc return null if they cannot fulfill the request of memory allocation. Recall the example that I shared at the beginning of this tutorial, where the students of your class are asked to create an array in the first year while predicting the number of students who might join in the next year. Till now, we have learned how to create an array dynamically, that is, based upon the user input, but we still have no idea how to predict how many students will be joining in the next year. This is where the function realloc comes to our rescue. Once an array is created dynamically using malloc or calloc, realloc can be used to change the size of the array as and when required. It extracts the content of the old array, deallocates it, creates a new array with the new size, and stores the data that it had extracted from the old array in their appropriate position. However, realloc does not work if the array is created statically. Let us take a look at an example to understand the working of the realloc. In this example, we first create a 5-celled integer array dynamically using malloc and store some values in it. The for loop in blue is responsible for storing data into the array. Note that we have stored I plus 1 into 10 in the ith cell of the array. This means if I is 0, I plus 1 will be 1 into 10 gives us 10. So 10 will be stored in the 0th cell of the array, 20 will be stored in the 1th cell, and so on and so forth. Next, we will display the contents of the array. Note that we had created a 5-celled array and stored data in those 5 cells. But now we will take a peek at the next 5 contiguous blocks as well. On executing till here, we get the output as this. Note that the first 5 cells are holding the values entered from the program, while the last 5 memory blocks are holding garbage values. Also note the starting address of the array ARR. Next, the control executes the colored lines of code. The realloc function takes 2 parameters. The first parameter is the name of the original array, while the second parameter is the size of the new array that needs to be created. On executing this function, a new array ARR new is created where the data of the array ARR is already copied, while leaving more space for the storage of further values. So after this statement is executed, it is expected that the cells 0 to 4 of ARR new will be holding the data of the array ARR. Hence, the for loop now works on storing some more data in the subsequent cells ranging from 5 to 10. Now when we display the content of ARR once again, we find that all cells of ARR is holding garbage. This indicates that the realloc function has actually deallocated the memory which was once assigned to ARR. Now when we display the content of the new array ARR new, there are a few things to note. Number 1, we find that the base address of ARR new is different from that of ARR, which indicates that a new part of heap has been assigned to ARR new. Number 2, the value of ARR has been copied onto the first n cells where n was the size of ARR. 3, all cells in the array ARR new are located contiguously with the cell size of 4 bytes. So the claims that we had made earlier regarding realloc function is proved. Now you might ask me that we could have done this easily by creating a new array using malloc and copied the contents of the old array into the new array and then freed the old array. Well, actually yes, we could have done that, but the number of lines involving it would have been 2 plus n, where n was the size of the old array. Moreover, I gave a separate name to the new array for you to understand clearly. We could have given the same name as the old array to the new array too. In that case, the output would have shown the similar observations as discussed, and it would require only one line of code instead of 2 plus n. For clarification, I will show you the same code once again, but this time the old as well as the new array will have the same name. Here lies the modified code for realloc demo, where the old as well as the new array has the same names. On displaying the output, recall the 3 observations that we had made earlier. Number 1, we find that the base address of the new array ARR is different than the old array ARR, which indicates that a new part of the heap has been assigned to the new ARR now. Number 2, the values of the old ARR has been copied onto the first n cells of the new ARR, where n was the size of the old ARR. Number 3, all cells in the new array ARR are located contiguously with cell size of 4 bytes. So the claims that we had made earlier regarding realloc has been proved. With that, we come to the end of this tutorial. Thank you for watching. Hope you have enjoyed it. Please hit the like button and share it with your friends. And don't forget to subscribe to my channel for more such tutorials. Stay home, stay safe. Bye-bye.